Okay, this lesson is for Unit 4, Lesson 1, and I know it says Part 1 there, but I actually think that adding, subtracting, and multiplying is all Lesson 1, and then division is Lesson 2. So Part 1, but Part 1 might be the only part that we have in this particular lesson. Without further ado, let's get going on adding, subtracting, and multiplying polynomials. So the first question we have here is, what is a polynomial? And I have here, this is a simple concept, but it's very hard to define. In fact, it's so simple that you actually already know a bunch of polynomials and you know how to add and subtract and multiply them because you've been doing it. But actually defining what a polynomial is in precise terms is really hard. If you go onto the Google and you just do a search for like a definition of polynomial, probably whatever comes up is going to freak you out because the actual definition, to get it well defined so that there's no confusion, there's no ambiguity, there's no way somebody could find like that one thing that like, well, what about this? And then it turns out your definition isn't good, is I usually don't go there, but finding a way to define a polynomial in a way that's like kid friendly, that's high school kid friendly, is not super easy. So this is what we're doing this year. Okay, so the prefix poly, if you think about like where other places you've seen the prefix poly, maybe polygon, means many. Okay. And I'm sure you can think of some other words that start with poly, but poly, the prefix, means many. Okay. So that leads us to the question, all right, many what? Polynomials, many nomials. Oh, that's helpful. That's not super helpful. So, so let's see what the answer is. The answer is many terms. Okay, so a polynomial is an algebraic expression that exists of many terms. Now, for a good number of you, we need to stop and we need to find what a term is, because it's not going to do you any good to think about, oh, many terms. Yeah, good. All right, so what on earth is a term? Well, terms are things that are added or subtracted. So polynomials are algebraic expressions that have many things added or subtracted. Now, there's like some other provisions that we have to get in there. A polynomial is an algebraic expression that can have many terms, but I need to point out it does not have to. There may only be one term in your polynomial. So the prefix poly is simply opening up the possibility that there could be many terms, but it's not a requirement for something to be a polynomial. It is possible that it will only have one term in it. Well, what else is there? That can't be the only thing. Just a polynomial is a bunch of stuff that's added or subtracted. True, but there are some other requirements that go with it. All the numbers in your polynomial, and by that we mean coefficients and the exponents. Okay, so you get a sense there that we're dealing with things that, like, yeah, coefficients and exponents must be real numbers. Okay, so polynomials are not going to have any i's in them at all. So all of the numbers that we deal with are going to be real. And the exponents have a specific requirement. They must be integers greater than or equal to 0. And so again, we run into the problem where if in the definition there's another word that you might not know, you have to back up and define that. I know that it's tedious, but again, like these words, if you don't know what these words mean and you don't know what they look like when you write them down, like when you start using them in the math, it becomes really problematic. Okay, so integers are these numbers here, like -4, -3, -2, -1, 0, 1, 2, 4, 5, and so forth. So when we say integers greater than or equal to 0, we mean that set, which I think is either the whole numbers or the natural numbers. I do get whole numbers and natural numbers, just kind of like I know, like I have to look up which one. One of them includes the 0 and one of them doesn't, and I can never remember which one is which unless it's something that I've looked up and studied recently. So yeah, so the exponents have to be integers greater than or equal to 0. And so there are no exponents that are going to be fractions. There are no exponents that are going to be negative, no decimal exponents. Now the coefficients can be, okay? So those can be like fractions or negative and so forth, but not the exponents, okay? This is getting to be a lot. Anything else? Well, yeah, one other thing. There can be more than one variable, but we will not consider those in this class. Okay, so there's nothing in the definition of polynomial that restricts it to just having one variable, say an x. You can have polynomials that have like an x and a y in them, but typically you would not even begin to look at those until a much higher level math class. So it's like one little provision in there. You can kind of forget that I said it. All right, so is there any good news about what on earth a polynomial is? So we know that a polynomial consists of many things being added and subtracted, and that all of the numbers in that expression have to be real, and the exponents have to be integers greater than or equal to 0. Why, yes, there is substantial good news. You are already familiar with loads of polynomials. We just haven't been using that particular vocabulary word. So you already have a really good basis for what polynomials are. Again, you just haven't used that word. So what we do in this lesson is we just build off of the things that you already know. You already know how to add and subtract and multiply polynomials, just maybe not like the ugly ones, but you know how to do it with the basic ones, and then all we need to do is extend that skill. So numbers actually qualify as polynomials. So if you had, say, the number 5, that could be written as 5x to the 0. Now, I really don't want to get into why x to the 0 is equal to 1, but it is. If you don't believe me, pause the video, grab a calculator. I want you to do like 3 to the 0, 4 to the 0, 5 to the 0. I promise you your calculator is going to tell you it's equal to 1 every single time. So x to the 0 also equal to 1. Numbers, lines, and quadratics are all polynomials. Okay, so the things that you've been studying in algebra, the things that you've been studying in this class fall under that heading of polynomials already. So you have a nice foundation for it. Okay, so first 10-ish minutes were just spent defining polynomials. We have a couple other vocab things to get through. So a few more vocabulary pieces to this. Some polynomials are much more common than others. So when you have certain kinds of polynomials that are much more common than other kinds of polynomials, we might have words specifically for those kinds of polynomials. And so I do have the 3 that are going to be over there under type, the number of terms, and then I'll give you an example of one. You will be familiar with these though. So the first type is something called a monomial. Now remember I said a few minutes ago that poly means that we can have many terms, but it wasn't a requirement. So a monomial, because the prefix mono means 1, and an example of a monomial might be something like a 5, something like an x, maybe like 4x. Okay, in other words, there's only one thing there. That's it. There's actually no adding or subtracting because there's nothing else to add or subtract it to. So it's just there. So you've actually been dealing with polynomials since kindergarten when you first learned numbers. You just didn't know that they were really, really basic polynomials. The prefix of bi means two, and so a binomial is a polynomial that has two terms, and you've seen all kinds of these when you've seen stuff like 2x plus 1 or x minus 5. Okay, and those are binomials because there are two terms. So you've got 1, 2, two terms. And then hopefully this last one is pretty straightforward. Prefix tri means three. So a trinomial is a polynomial that has three terms, and pretty much all of your standard form quadratics would fit that description. So you have x squared, negative 2x, and 4 are the three terms, and 3 is tri. There you go. Now, past trinomial, we don't have specific vocabulary words for it because those are not always, they're not anywhere near as common. So if you have something with 4 terms in it, there's a chance it's what's called a cubic polynomial, but there's no specific word for those. Okay, so these are just like specific words for yeah, the common ones. So 11 minutes. 11 minutes kind of define what a polynomial is and get that vocabulary out there. I think you'll develop a more comfortable sense of what polynomials are once we just start working with them. Okay, so adding polynomials, you simply combine like terms. That's it. That's all you do. So here's an example of one. So we are going to combine negative 3x to the third plus 2x squared minus 4 plus 2x to the third minus 4x squared plus 3x. And when I do this, I like to circle my like terms. So I have negative 3x to the third plus 2x to the third, and just pay attention to the operator there. So the 3x to the third is negative and the 2x to the third is positive. So when I combine those, I will get negative 1x to the third. Then I have 2x squared minus 4x squared. So 2x squared minus 4x squared would give me negative 2x squared. And then my other two don't match. So I have a minus 4 and a plus 3x, and they are not the same. So they're just going to come down, and I am going to put the x next and then the 4 last. So that my final answer is in what's called standard form. And that just means that the exponents are going to count down. So I have 3, 2. Now, we don't write the exponent of 1, but there is an exponent of 1 right there, x to the first power. And then I mentioned earlier that x to the 0 actually is there. We never bother to write it, or very rarely would we bother to write it. You do not have to write it, just so we're clear on that. Now, you might want to line this up vertically. So you might want, if that is better for you, so you might do something like negative 3x to the third plus 2x squared minus 4, and then line it up so that your x cubes are underneath each other. You might run into a problem though, like right here, because those aren't like terms, but I'll leave that up to you whether or not you want to set the problem up like that, or if you're just good writing it out side to side. And just be careful for careless mistakes. So now you try one. Pause the video if you're doing this as a makeup assignment from being absent, or in the case of the year that I'm recording this, you might be doing this because you missed the lesson because you were doing a makeup test. Hopefully that won't be the case every year, but pause the video, do this one out in your notes, and then unpause the video to check your answer. Okay, so I'm going to go ahead and remove my parentheses. And this is a formality. You do not need to do the separate step of removing your parentheses. But when we get to subtraction, you do want to make sure you're taking care of that. Okay, so I have 2x to the fourth plus 1x to the fourth. So that's going to give me 3x to the fourth. I have a negative 2x to the third. That's all by itself. There's nothing to combine with that. I have 3x squared plus 2x squared, which is going to give me 5x squared. I have negative x plus 4x, which is going to give me 3x. And then last but not least, I have 1 minus 5, which will give me minus 4. Now, if you got it wrong, remember, I say this all the time, this is really, really low risk. There's nothing bad that happens if you got this wrong. Just take a moment and go back and look over your work and try to see what was your mistake. Did you combine the x to the third with something that wasn't an x to the third? Did you make an arithmetic mistake? Did you make a sign error? Do you feel like, oh, I got the right idea, but I added wrong? And take that moment to try to figure out what was it that you got wrong in the problem. Right, so subtracting polynomials. Just be sure to distribute the subtraction to the whole polynomial. We have covered that with complex numbers when we did the complex numbers. So this is where I would highly, highly, highly recommend that you do remove the parentheses in a separate step. As of the recording of this, I have just recently graded the quadratics test, and a lot of students did not bother removing the parentheses on the subtraction of the complex numbers, and that causes mistakes. So it doesn't take that long to do it. So remember though that what I'm talking about here, this subtraction goes with the entire polynomial that follows. And so we're going to be subtracting 2x to the 5th. We're going to be subtracting negative 6x to the 4th. We're going to be subtracting negative 3x, and we're going to be subtracting 7. When you subtract a negative, the opposite of the opposite is the original expression, which in this case would be 6x to the 4th. And then we'll have plus 3x, and then we will have a minus 7. Now, once in a while, a student will say to me, well, so what you're doing is like the subtraction flips the sign of everything in the second parenthesis. Yes, but that's an awful way to conceptualize it. So yes, it does flip the sign of everything, but it's important that you know that it flips the sign because you're subtracting everything. So now combining our like terms, we have 3x to the 5th minus 2x to the 5th, which just gives us 1x to the 5th, or x to the 5th. We have negative 2x to the 4th plus 6x to the 4th, so that'll give us 4x to the 4th. I don't have any x to the thirds anywhere in this problem. I don't have any x squareds anywhere in this problem. So I guess we just bring down the plus 3x minus 7. There wasn't anything more to do with that particular problem. And you try one. So as always, pause the video, try to work it out on your own, and then unpause the video to check your work. Okay, so I am going to take that separate step and remove the parentheses. And again, the thing you need to remember about removing the parentheses is that you are subtracting everything in that second set, which does indeed flip the sign of everything in the second set of parentheses. I am really, really warm right now, if you're wondering why I keep like moving my hair off my neck. Went to the doctor earlier today and I had to take a prescription for something, some vertigo issues, and I think it's making me look really warm, so that's not cool. Okay, let's combine some like terms. So we've got negative 3x to the third minus 4x to the third. So those are both negative, which when you combine them makes them even more negative. So negative 7x to the third. We have positive 2x squared minus 3x squared, which will give us negative 1x squared. You do not need to put the 1 there. We have negative 5x plus 7x, which will give us positive 2x. And then last but not least, positive 1 plus 2 gives me 3. Again, if you got it wrong, there's like nothing awful about getting it wrong, but notice what your mistakes were. Take that time to see what was it that you did wrong, and like how can you avoid that mistake in the future. Okay, so do pause the video and give yourself time to think of that through. Now, for multiplying polynomials, we are in the last 4 slides. Okay, so there's not, and I think the last slide is just what is your homework, which I don't know what it is, but for multiplying polynomials, okay, we do need to do a quick review of the laws of exponents, because when you're multiplying things that have higher exponents, it's important to make sure you know what to do with those exponents. So let's say you were multiplying something that had x to the 4th and x to the 3rd. What should you do with those exponents? Are we going to get x to the 12th? Are we going to get x to the 7th? What are we going to get? Okay, so here's how you can reason it out. The reasoning is important because you absolutely will forget shortcuts. Okay, we are not doing shortcuts. You need to know why something works. So think about what this problem is. It is x to the 4th times x to the 3rd. Going back to the definition of what an exponent is. An exponent tells you how many times that particular expression is used as a factor. So if you have x to the 4th, what that is shorthand for is x times x times x times x. If you have x to the 3rd, that is shorthand for x times x times x. Now, what's the operation? So here's the x to the 4th, here's the x to the 3rd. The operation in between them is another times sign. So what do I actually have here? I have x times x times x times x times x times x times x. I have 7 x's all being multiplied together, which means this is x to the 7th. And what you'll notice is that we added the exponents. Now, I picked x to the 4th and x to the 3rd randomly. You could try this with x to the 5th, x squared, x to the bajillion. I wouldn't, it'll take up too much space, but you can do this with any exponents that you have. So whatever exponents you have, you can expand them and then actually look at it and see, oh, that's right, like I should add these together. So what do we get from that? Well, what do we do with the exponents when we multiply like bases? We add them. And if you're wondering, what was that, Miss Taylor? Like bases just means that we're multiplying all x's together. Okay, so we don't have x to the 4th and y to the 3rd, because those are not the same. All right. So let's do an example. We're going to do a couple of examples here. Now, I do want you using the area model, and that's not because I'm trying to be a pain in the neck. It is more organized and space efficient than repeated distribution. So even if you've learned how to do this before with repeated distribution, I promise you the area model is going to lay out the work better. It's a lot less error prone, and it's going to take up less space on your page. Okay. Just be sure when you're using the area model that you write the whole answer out at the bottom. Don't just fill out the area model and be like, oh, I'm done. You do need to write the answer from that. So because I'm a glutton for punishment, I gave myself this one to do. X to the 3rd plus 3x squared minus 4x plus 1 times negative 2x squared plus 2x minus 3. So let's go ahead and we'll set up a nice generous area model there. And we have x to the 3rd, 3x squared, negative 4x, and 1. And then going down the side, we'll have negative 2x squared, 2x, and negative 3. Okay, and the way the area model is going to work is to find the area of the whole thing. We're going to find the area of each of the little individual rectangles there, and then add them all up. Okay, easy peasy, right? So we have going across the top here, negative 2x squared times x to the third. Now remember what we just went over about the exponents. You're going to add those exponents together. So we're going to get negative 2x to the fifth. Next one over is negative 2x squared times 3x squared. And again, we're going to add these exponents together. 2 plus 2 is 4. And so that'll be negative 6x to the fourth. Next one, negative 2x squared times negative 4x. Well, a negative times a negative is going to give us a positive. And x squared times x to the first is x to the third. So this will be 8x to the third. And then hopefully you're okay with negative 2x squared times 1. That'll just be negative 2x squared. Okay, next line down, 2x times x to the third. X to the first times x to the third would give us x to the fourth. So this will be 2x to the fourth. Next one is 2x times 3x squared. So that'll be 6x to the third. Here we have 2x times negative 4x. So that'll be negative 8x squared. And 2x times 1 is just 2x. Last one, negative 3 times x to the third is negative 3x to the third. Negative 3 times 3x squared will be negative 9x squared. Negative 3 times negative 4x is positive 12x, and negative 3 times 1 is negative 3. Ta-da! Now, we have to add them all up. So I want you to notice something. What do you notice about the like terms? So we do need to combine all of the like terms, which means we need to combine x to the fifth with other x to the fifths and x to the thirds with other x to the thirds. So I'm going to pause for a moment and just let you look at the array there and see, like, do you see patterns for where the like terms are? All right, hopefully what you noticed is that the like terms are laying on the diagonals. Okay, so you have like 2x to the fourth and negative 6x to the fourth. Here, right on that diagonal, are all your x to the thirds. Here are all your x squareds. Here are your x's. And then in the upper left and the lower right, those are the things that don't have anything that matches. So what you might notice is that they are on the diagonals. So the 2x, negative 2x to the fifth is all by itself. So that's an easy one. Negative 2x to the fifth. And you can use a calculator for this if you want. Whoops, don't do that. There we go. Negative 6x to the fourth plus 2x to the fourth is negative 4x to the fourth. When you get to the threes, yeah, a lot of you might want to use the calculator. This will be 14x to the third, and 14 minus 3 is 11. Here we have all negatives. This will be negative 10x squared minus 9 gives us negative 19x squared. I'm going to run out of space over here. 12 plus 2 is 14. So 14x minus 3. So remember I said up here, just be sure to write the answer out at the bottom, minus to the side because I had stuff at the bottom, but negative 2x to the fifth minus 4x to the fourth plus 11x to the third minus 19x squared plus 14x minus 3. Now notice that the like terms are on the diagonals. So that brings us to this, okay? So we're going to do this one, and I'm going to go ahead and set up my area model, and I have 2x to the third, 3x, and negative 4, and then 2x and 4. And let's go ahead and multiply these through. So 2x to the third times 2x would be 4x to the fourth. 2x times 3x is 6x squared. And 2x times negative 4 is negative 8x. And then my bottom line here, 4 times 2x to the third is 8x to the third. 4 times 3x is 12x, and 4 times negative 4 is 12. Okay, I did that bottom line fast, so pause the video if you need to. And what you might notice on this one is that our diagonals don't quite match up right. So that nice little pattern that we saw there, okay, isn't quite holding. We do have the 4x to the fourth, and there's no other x to the fourth. But right here, we do have that break in the pattern where we have an x squared and an x to the third on the diagonal. This one lines up okay. So that one is okay. And then the 16 is by itself. So when I go to write my final answer for this, I have 4x to the fourth, but then I can't combine these. So they just have to come over as is. Plus 6x squared. Now I can go ahead and combine the linear terms or the x terms. 12x minus 8x would give me 4x. And then minus 16. So if you're having trouble seeing that, it says 4x to the fourth plus 8x to the third plus 6x squared plus 4x minus 16. Okay, and yeah, so there is, I do have a question right here. Okay. Like terms will be on the diagonals if the original expressions were not missing any terms, and I have the missing, like that's arbitrary. But if you look at this top one right here, okay, notice that it starts with x to the third, and after x to the third would be x squared, but there's no x squared there, and so that's what I'm referring to as like a missing term. So if you have terms that are missing and they don't go in order, that's going to mess up your diagonals. But if you're not missing anything, then your diagonals should line up, which is another advantage to the area model. And even when they don't quite line up right, they're not going to be far away from each other. So you're not going to see like an x squared here and another x squared far away from it, which you will if you do repeated distribution. So please use the area model. It is very, very user friendly. All right, so this is the last one. You try one, but before completing the problem, do you think the like terms will be on the diagonals or not? So take a look at what I just said, take a look at the problem you have, and just think to yourself, okay, are these going to be on like terms or not? Pause the video, work the problem out, and then resume the video, and we'll go over it. All right, let's do this. Let's see, we've got, what do we have? We have 2x squared minus 4x and a positive 1. And then this is negative 3x squared minus 2x and a 5. And I will go through this pretty quickly because I am assuming that you've already done it and you're just checking work and you're not frantically trying to copy my work. Don't do that. Upper left, this will be negative 6x to the fourth. And then a negative times a negative will give us a positive 12x to the third. And this will be negative 3x squared. Negative times positive is negative. So this will be negative 4x to the third. 8x squared and negative 2x, and this will be 10x squared, negative 20x, and 5. And then you might notice that, yes, your like terms are on the diagonals here. So you have your x to the thirds, and you have your x squareds, and you have your x's. I'm being a little sloppy with that. All right, so our final answer would be negative 6x to the fourth plus 8x to the third. What is this one? Plus 15x squared minus 22x plus 5. Hopefully I didn't obscure something with my circles there. I'm like a little afraid that I did. So I like double check my answers. Do I like what I wrote? Yeah. Okay. All right. So there you go. And now, typically, I'm going to look for your answers like below the box. I wrote it up there because that's where I had space to write it. So if you're going to write your answer in an unconventional space, at least be honest about it. Okay, so that was a definition, a kind of a long, laborious definition of polynomials, adding them, subtracting them, and multiplying them. And we threw in a little bit of a review on the laws of exponents, all in under 55 minutes. I feel accomplished with that. Homework is in OneNote. It will be. It is not there at the time I'm recording this, but I'm recording this over a break. So, but it will be there by the time you need to do it, and it will be due next class. So hopefully this lesson helped. And for those of you that are absent for it, that you are able to get caught up. Let me know if you have any questions.